Okay, welcome back. So, I guess for the next 2 lectures, I'll just have normal lectures, and then I guess next Tuesday, I think maybe I'll do like a half lecture, and then there will be 1 presentation, and then there will just be more presentations for the rest of the semester. And then I also reserved a room on May 5th for like a long series of presentations, because there were way more people who signed up than I expected, but that's good. But we'll have to do some during the reading period. Okay, and I'll try to maybe tomorrow send out like a schedule of who's presenting when. So today, I want to talk a little more about promotion in the setting of an area called dynamical algebraic combinatorics. So this is, I would say, an area that studies dynamical systems defined on objects for algebraic combinatorics. So the basic setup you might consider, this is dynamical algebraic combinatorics. So the basic setup here is we have some set X is a set of some interesting combinatorial or algebraic objects. And we have some function mapping this set to itself. So we have some map f from x to x, and we want to just iterate this map and see if there's interesting stuff that happens when we iterate it. So I'm going to look at promotion, which we've defined already on the set of linear extensions of a finite coset. So I'll remind you one definition we have for this. So we said, okay, here P is a finite coset. And L of P is the set of linear extensions. P. So these are bijections from, so let's say P has size n, so an n element coset. Then L of P is the set of bijections from P to the numbers from 1 to n, with the property that whenever x is less than y in the poset, then the image of x has to be less than the image of y as numbers. And we define promotion to be what you get by taking this composition of these Bender-Knuth involutions, b case of n minus 1 through b case of 1, as you do it in this order. And here, the way we define this Bender-Knuth involution was, so b case of I acts on a linear extension by saying, you look at the labels I and I plus 1, and if they're sitting on incomparable elements, then you swap them, and otherwise you do nothing. So here, b case of I, does this map from L, or okay, I'll just say b case of I of sigma. So sigma is a linear extension. This is defined to be, well, it could be where you swap I and I plus 1, which would be this, and that is if sigma inverse of I and sigma inverse of I plus 1 are incomparable. And it's sigma otherwise. Okay. So one natural question you can ask about, well, really any map here, like in dynamical algebraic combinatorics, if it's an invertible map, and ProMotion is an invertible map, you can ask about its order. So this would be like, what you could think of it as the least common multiple of all of the orbit sizes, or in other words, it's the smallest positive integer such that if you apply ProMotion composed with itself that many times, then that's the identity map. Okay, so I'm not going to prove really anything here, but I just wanted to mention some theorems that have been proven about ProMotion. So the first theorem is due to Schütz and Berger. From 1977. And this says, if you have a rectangle poset, which is really just the poset associated to like a rectangle-shaped Young diagram. Okay, so if P is a rectangle, okay, so the picture would be something like so that's like a rectangle poset drawn as a Hasse diagram. So if P is a rectangle, then the order of ProMotion is just the size of P. So it's like a very nice number. It's just saying the order is exactly the number of elements of the poset. Maybe I'll mention that this is kind of surprising because if you just find like whatever poset, just some random poset, and you just run a computer like iterating ProMotion, it's probably going to do some crazy stuff. It's probably not going to have like nice behavior. But then this is showing that like for a rectangle poset, there's something very nice that's happening. I'll just mention a few other posets where it's known that something is nice. Okay, so this theorem is due to Edelman and Green, and it's related to this fact that I mentioned before about the number of reduced words for the decreasing permutation in Sn, where that was like related to doing ProMotion on a staircase-shaped Young diagram. So this is Edelman-Green from 1987. So if P is a staircase, by that I mean, it's the poset associated to the staircase-shaped Young diagram. So I guess if I drew it as a poset, it could be something like that. In this case, the order of ProMotion is 2 times the size of P. So it's again a nice number. And then there is a theorem of Heyman from 1992 that gives 2 additional families where things are nice. So this is Heyman from 1992. Okay, so if P is this is a shifted double staircase, and it doesn't really matter like what exactly this is. I'll draw a picture of an example. Okay, so what is a shifted double staircase? It's something that looks, I think something like Yeah, okay, so basically you have some kind of, you can sort of imagine you've got some kind of staircase thing and you're allowed to like chop it here and like put it into this kind of shape. It's sort of this weird, I don't know, whatever the shape is. Anyway, it doesn't really matter. So if it's a shifted double staircase, or, okay, there's another family, a shifted trapezoid. Okay, what is a shifted trapezoid? It looks something like this. So you have like okay, so something, okay, it doesn't matter what the shape is, but it's something where it kind of looks like a trapezoid, like this. So in both of these cases, ProMotion has order 2 times the size of the coset. And for a while, since 1992, these were like the only families really where it was known that ProMotion had like a nice order. So it was kind of like, I mean, okay, there are like trivial examples. You can construct like, if you have like an anti-chain is a poset where like there are no edges in the Hasse diagram. Yeah.
Wait, yeah. So these posets don't correspond to the young tableau,
right? Yeah. These don't. Right. Yeah. I mean, maybe you can make them like shapes. You can put them as boxes, but they're not going to be like normal shapes. Yeah, like corresponding to partitions. Yeah. So these are just some posets. Yeah, but for a while, like these were sort of like the only families where it was known that ProMotion had like nice orbit structure, and then for like pretty much every other poset except in trivial examples, you know, things are just like very complicated. But actually, just a few years ago, there was another example that was found. So this was by Sam Hopkins and Martin Ruby. Ruby from, I want to say 2022, yeah. So they consider if P is what they call a chain of V's, okay, so what is a chain of V's? It looks like this. You have like a bunch of V's kind of stacked on top of each other. And then you have these edges here. You can imagine this grows higher. So you have some number of V's stacked on top of each other. In this case, it's again 2 times the order of the poset, or the size of the poset. Then so I guess like one of the sort of games in this field is like, okay, can you find examples of like interesting combinatorial dynamical systems where something nice actually happens? And like these are sort of the 5 families where something nice actually happens for ProMotion, but then like most other posets give you something crazy. I also want to talk about something more refined for the rectangle poset, because okay, so here I'm just saying like ProMotion has a bunch of orbits, right? So it's acting on this finite set, so it breaks up the set into these orbits. And the least common multiple of the orbit sizes is the order, which is the size of p. But you could ask for more refined information about like what actually are these orbit sizes. And so I want to talk about that, but I think first let me sort of go back to the representation theory context and just state the Hooke length formula, because I think I've maybe stated this before. I'm not going to prove it, but it's like important that we at least talk about it, and then I'll relate this back to promotion for the rectangle. So theorem. So this is the Hooke length formula. So you have a Young diagram of some partition shape, and you want to know how many standard Young tableau it has, because that's the dimension of the corresponding irreducible representation of Sn. Right, so let lambda be a partition of Sn, or of n. Then recall that we let f lambda be the number of standard Young tableau of shape lambda. We want to know, like, what is this? So if we have, so let's say we have our Young diagram. Okay, maybe here. Then for each box, we can define its Hooke length. Okay, so we go to some box, and the Hooke length is just you draw a ray from that box going to the east, and you draw a ray, maybe I'll do it in a different color. You draw a ray going to the east, and you draw a ray going south. And the Hooke length of this box is just the number of boxes that intersect these rays, which in this case is 4. Okay, so here, like the Hooke length of this box would be 4, and we could fill in the Hooke lengths of all the other boxes. Here it would just be like 1, because you only get that. Here it would be 4, because you get these. Here it would be 1, 2, 3, 4, 5, 6. Here it would be 1, 2, 3, 4, 5, 6, 7. This one would be 5. This one's 4. This one's 2. It's just these two. This one's 1. This one is 3. This one's 1, and this one's 2. So we have all these Hooke lengths, and then the theorem is that f lambda is equal to n factorial divided by the product, and I guess maybe I'll write this as like the product over b in lambda, and so what I mean is b is a box in the Young diagram of lambda, and this b has some Hooke length, which I'll denote by h sub b. Okay, and that's the formula. So it's a very nice product formula. So as an example here, okay, like what is in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So like in this example, the number of standard Young tableau, f lambda here would be 12 factorial divided by, okay, 7 times 6 times 4 times 1 times 5 times 4 times 2 times 4 times, wait, is this actually, yeah, okay, 4 times 3 times 1 times 2 times 1. Okay, so yeah, I guess I'm not going to prove this. There are various proofs that are known. Some are like probabilistic, some are more like bijective. But I want to come back and relate this to promotion on the rectangle. So let me make a definition, which is due to Reiner, Stanton, and White. So let X be a finite set. Okay, or maybe I should say, okay, definition due to Reiner, Stanton, and White. I think this was 2004, I think. So, yeah, let X be a finite set. Let F from X to X be a bijection. So this is some map that we're going to want to iterate, and let's say it's a bijection, let's say of order omega. Okay. And I'm going to pick a polynomial in a variable q. So let f of q be some polynomial in a variable q. Let's say, yeah, I guess with complex coefficients. Then we say that this tuple x little f and capital F of q exhibits the cyclic seeding phenomenon. If okay, so if for every integer k if you want to look at, if you look at the number of elements, the number of elements of x fixed by the kth iterate of f, so f to the k, f composed with itself k times, the number of these elements is what you get by evaluating this polynomial capital F at a k, oh yeah, at the, well, at e to the 2 pi I k over omega. Okay. So, well, yeah, let me do an example of this. Yeah, maybe I'll do the example over here. So let's look at promotion for, let's just take this this rectangle, a 2x3 rectangle. So okay, what does it look like? Okay, well we can have, let me just draw all the cosets. Okay, so we could do 1, 2, 3, 4, 5, 6. And then I think this goes to, well, okay, we could just do it. If I do the Bender-Knuth involutions, the 1 and 2 does nothing, the 2 and 3 does nothing. I swap the 3 and the 4. So I'm gonna have 3 over here. And then I swap, the 4 is here now, so I swap it with the 5. And then the 6 doesn't go anywhere. Okay, so yeah, that's what I wanted. I think then down here we're gonna get 1, 3, 4, 2, 5, 6. Does that make sense? Yeah, the 2 and the 3 swap, and then the 3 stays the same, and then the 4 swaps with the 5. Yeah, okay. And then this goes back here. So we have this 3 cycle, and then over here we have 1, 2, 4, 3, 5, 6, which maps to 1, 3, 5, 2, 4, 6. And this goes back here, so you have a 2 cycle. And I want to use this polynomial, so I'm going to let f of q be 1 minus q plus q squared times, well, let me write it down. Let f of q equal 1 minus q plus q squared times 1 plus q squared plus q cubed plus q to the 4th. Then you can check just by plugging in numbers. That so f of, well, actually first I should do, okay, f of e to the 2 pi I, yeah, let's just say 1 over 6. Okay, so 6 is the order, right, because it's the least common multiple of 3 and 2. So I want to use omega equals 6 over there. If I plug in f of e to the 2 pi I over 6, I guess if you do this, you'll end up getting 0. And 0 is the number of these standard or linear extensions that are fixed by just f itself, right? Because none of these are fixed. So that makes sense that this is 0. If you plug in e to the 2 pi I times 2 over 6, you'll end up getting 2. And 2 is the number of things that are fixed by f squared, because f squared, well, it'll send like here to here, and then that's not fixing it. It'll send this one here, which is not fixing it. It sends this one here, which is not fixing it. But these two get fixed, right? F squared will just send this to itself, and it'll send this to itself. So there are 2 things that are fixed by f squared. And then we can keep going. F of e to the 2 pi I times 3 over 6 ends up being 3, and that's because these 3 elements are fixed by f cubed, but these are not. F of e to the 2 pi I times 4 over 6 ends up being 2, because these 2 elements are fixed by f to the 4th, but these are not. If we do the 5th power, so e to the 2 pi I 5 over 6, this ends up being 0. None of these are fixed by f to the 5. And finally, f of e to the 2 pi I times 6 over 6. Well, actually, this one's easy to do. So this is just e to the 2 pi I, which is 1. So f of 1, we could just evaluate this should give us 1, and then over here, oh, did I miss something? Ooh. No, okay, sorry, this is fine. Yeah, this gives us 5, right? So it's 1 times 5, and there are 5 elements here, and so all of them are fixed by f to the 6, because 6 is the order. Okay. So, okay, I mean, I stated this for all integers k, but really you just need the integers from like 1 up to omega, because everything is periodic. So if I did this for like, for k equals 7, I would just get 0 again, and we would just repeat this. So, so this is showing that, okay, so promotion, well, sorry, okay, it should be the set of linear extensions of this coset. That's my set X over there. And then the map is promotion. And the polynomial is this particular f of q. So this exhibits the cyclic sieving phenomenon, which I'll abbreviate as CSP. So I guess the point of this is that, like a priori, if you just have some map from the set to itself, it could have like a lot of different orbits of different sizes, and like one way you could encode the orbit sizes is to just list them out, but that might be like a long list of numbers. Okay, here it's just 3 and 2, but like in general, it could be like you've got 100 orbits of size 10 and like 27 orbits of size 5 or whatever, and so listing it out might be complicated, but it's nice if you can find just a simple polynomial that you can write down in some compact form that's actually encoding all of the orbit structure. Because like basically if you know this polynomial and you know the order, you can recover all of the orbit sizes. So it's encoding it in this nice compact way. Or I guess I should say, like if you just hand me a map F, like an invertible map from a finite set X to itself, and you ask like, okay, is there some polynomial so that this satisfies the cyclic sieving phenomenon with respect to that polynomial? I would say yes. The answer is always yes. There's going to be some polynomial, and you can find it by just doing some kind of like polynomial interpolation thing. You could just like construct it in some way, but probably what you get is just going to be some garbage. Just it's going to be gross. So what's nice is that like in the cases when you can actually describe this polynomial in some very compact way. And one of the cases where you can describe it in a very nice compact way is when we look at promotion on a rectangle. So let me also just mention that, like whenever I have this cyclic sieving phenomenon, if I plug in q equals 1 into this polynomial, I should get the size of x. So note that f of 1 needs to be equal to the size of x. For example, like by setting k equals 0, right? Like if k is 0, then that's f of 1, and that needs to be the number of elements fixed by f to the 0. Well, f to the 0 is the identity map, so it should fix everything. So the number of elements fixed by the identity is just the size of x. Okay, so, I need a little bit of notation. So so this is sort of standard notation that's used in a lot of places. So, bracket, let's say I, so I is some, let's say positive integer. Bracket I, so q is going to be 1 minus q to the I divided by 1 minus q. Or you can just write this out as like 1 plus q squared plus da 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 plus q to the I minus 1. And then also let bracket k factorial q. This is defined to be the product of these, so this is like the q analog of I, is what it's sometimes called. And then this is like the q analog of k factorial, and by that I mean it's like the q analog of k times the q analog of k minus 1 times times q analog of 1. So just all the integers from k down to 1. Right, so this would be like 1 minus q to the k over 1 minus q times 1 minus q to the k minus 1 over 1 minus q, and so on to 1 minus q over 1 minus q. Okay. Okay, so here's what I want to do. So this is a theorem of Brendan Rhodes from 2010. Okay, so let's let lambda, well, okay, maybe I'll let p. Okay, let p, well, okay, do I want to do it this way? Okay, maybe I want to do it as a Young diagram. It's the same thing, right? Like here I'm looking at like a rectangle poset, but it's the same thing as a rectangle Young diagram. We can go back and forth, so I'm going to do this in terms of Young diagram. So let lambda be a rectangle shaped Young diagram of size n. So within boxes, I guess I can say. Within boxes. So we can consider this set of standard Young tableau of shape lambda, and we've defined promotion on this set. And what I want to do is find a polynomial that I can put here so that I can say this exhibits the cyclic sieving phenomenon. And if I can put some nice polynomial here, then that'll encode the entire orbit structure of promotion acting on this rectangle poset. So, sieving phenomena. And there's sort of an obvious guess for what you, or maybe not obvious, but there's a guess that you could make, because I need some polynomial in Q, and I need it to be the case that if I set Q equals 1, then I should get the size of my set, which is the number of standard Young tableau of shape lambda. And we know that the number of standard Young tableau of shape lambda is given by this hook length formula. So what you could try to do is just take the pieces of this and like Qify them so that you replace each piece with a polynomial that specializes to that number when you set Q equals 1. And it turns out this is like the right thing to do. So what you end up doing is, so you take the Q analog of n factorial, which is this thing, and then you divide by the product over all of the boxes in lambda, and you just take the Q analog of the hook length, which is like this thing here. And magically this ends up working, which I think is kind of very nice. Right, so now this is like some very compact formula, and it's describing the entire orbit structure of promotion on this like large set of standard Young tableau. Yeah, so I think this is very cool. Let's see, what else do I want to say about this? Oh, one thing you might ask is like, what if it's not a rectangle shaped Young diagram? What if you just take a different Young diagram? Because then we still can define promotion. We still have a hook length formula, so you might say, well, what if like the same exact thing just works? And it turns out it doesn't, somehow. So it's actually complicated to try understanding the orbit structure of promotion on general Young diagrams. But for rectangles, it's very nice. And actually, I think even for staircases, I think maybe there's like a conjectured cyclic sieving phenomenon that hasn't been proven, something like that. But anyway, we understand rectangles. Any questions about this? Okay, so I also want to talk about a different perspective that I've been thinking about for the last few years that I think is kind of cool. So I call this combinatorial billiards. So if you know, like from dynamics, like in the field of dynamics, one thing that people do in dynamics is they have some map and they iterate the map. And they look at, okay, what happens if you iterate this? So, people do this with like population dynamics and like ecology and stuff, but then they do it in like more number theoretic settings. Maybe you have like an algebraically defined function and you want to understand like number theoretic properties if you iterate it. So there are a lot of different like maps that people iterate, and you can think, okay, what I've been talking about here is like, this is the sort of combinatorial version of things. But another thing people do in dynamics is they look at billiard systems. So in billiards, you have like there are a lot of different variants of billiards, but like one of the classical settings that people consider is you have some region, maybe in the plane, or it could be in more complicated spaces, and you shine a beam of light in some direction inside of this region. Right, so you shine your beam of light, and then when the beam of light hits the boundary, it reflects, and it does this so that like the angle of incidence equals the angle of reflection, just like in normal physics, how light reflects. And so you end up getting maybe like some crazy thing where it bounces around, like whatever. Okay, and then people try to understand like what is the dynamics of this. So in combinatorial billiards, I want to study like billiard systems that are very sort of combinatorial and rigid, and then maybe we can say things about them using combinatorics or algebra. And one of the main things that led me to consider this, and also some other people as well in the last few years, is we realized that like promotion is actually a billiard system. So I want to explain how promotion can be seen as like a beam of light bouncing around in some space. So yeah, let me draw a picture of this. And okay, it's kind of hard to draw the pictures because I can only draw things in 2 dimensions, so I'm going to do a very simple example, but then I'll try to explain that actually this works in higher dimensions too. So here's my picture. Okay, I want a hexagon. That's a pretty good hexagon. Okay, so I have my hexagon, and there's a natural way of associating these 6 triangles with the 6 permutations in S3. Okay, so these are like 1, 2, 3, and 2, 1, 3, or okay, maybe let's do 2, 1, 3 here. 2, 1, 3, 1, 3, 2, here 3, 1, 2, 2, 3, 1, and 3, 2, 1. I can explain maybe more in a minute how you get this, but basically the rule is that, so I picked some triangle to be the identity permutation, and then passing into an adjacent triangle corresponds to swapping two adjacent numbers. So swapping like I and I plus 1 for some I. So here I swapped 1 and 2, here I swapped 2 and 3, here I swapped 1 and 2 again, here I swapped 2 and 3, here I swapped 1 and 2, and then I swapped 2 and 3 again. So I want to take a poset, and my poset has to be very simple in order for me to draw it in 2 dimensions. So I'm going to take my poset to be this 3-element poset. In general, for what I'm going to describe, the dimension of the space where I'm working is going to be 1 less than the number of elements of the poset. So because I want to work in a 2-dimensional space so I can draw things, I have to work with a 3-element poset. So here's my poset, and it has 2 linear extensions, which are sorry. I want to assume that the elements of my poset are the numbers 1, 2, and 3. Okay, so this is not a linear extension yet. This is just saying like the elements of my poset are 1, 2, and 3. And then I'll draw the same poset again. And now there are 2 linear extensions. So I could label it as like 1, 2, and 3, or I could label it as, let me get one other color. 1, 3, and 2. And so I'll think of the red one as the identity permutation, because it's like it maps 1 to 1, it maps 2 to 2, and it maps 3 to 3. So that would be this over here, 1, 2, 3. And then this one is the map sending 1 to 1, sending 2 to 3, and sending 3 to 2. So this is the permutation 1, 3, 2, here in green. And I want to consider these 2 triangles because those are the linear extensions of my poset. So geometrically, I can think of the set of linear extensions of my poset as these 2 triangles. So I'm going to focus on those 2 triangles. Okay, so maybe I'll do this. So I have this rhombus region here. And one thing I'll mention is that, okay, so I have some union of triangles, which is a convex set, right? So this rhombus here is convex in the usual geometric sense. And in fact, if you choose any union of these triangles, which is convex, then that will be the set of linear extensions of some poset. And in fact, every set of linear extensions of a 3-element poset arises in this way. And there's a more general version of this where you can do this in higher dimensions. And then it turns out like convex sets of these regions correspond to linear, or sets of linear extensions of posets. So this is kind of a nice geometric perspective for thinking about linear extensions of posets, because now it's just like some geometric object. So what I want to do is, let me remind you, okay, promotion. So what is promotion? Well, it's this composition of these Bennard-Knuth involutions. I actually want to add on one extra Bennard-Knuth involution, which I'll call B case of in, but I'm just going to declare B case of in to be the identity map, so I'm not actually changing anything. So it might seem like a stupid thing to do, but there will be a reason for this. So B case of in of any linear extension sigma is just sigma. It just always fixes everything. Okay, and of course if I add that here, it doesn't actually change ProMotion, so this is still fine. So what I want to do is apply ProMotion iteratively, starting at, let's say we start at this linear extension. Okay, so I start at this linear extension, which I'll imagine is like this point in the 1, 2, 3 triangle. Sometimes these little triangles are called alcoves, so I might also call them alcoves. So I'm starting at this point in the 1, 2, 3 alcove. And now I want to do ProMotion. So I'm going to start by doing BK sub 1. So to do BK sub 1, I look at the labels 1 and 2, and I say, well, the 1 is below the 2, so I can't swap them. I just don't do anything. But I want to think about doing nothing as the following. It's kind of like I was trying to swap the 1 and the 2, but this edge is sort of getting in my way, and it's keeping me from swapping them. So it's like I want to swap the 1 and the 2, but I'm not allowed to. And over here, I want to think, okay, if I did swap the 1 and the 2, I would move over to here. So I would move over here. But I'm not allowed to. I'm not allowed to basically leave this blue region here. This is like my linear extensions, and I can't leave this. So I'm trying to go over here, but I get sort of rejected when I hit the boundary here, so I end up bouncing. And so it's like I have bounced off of the boundary of this blue region here. Okay, so that's like BK sub 1, this little movement here. Okay, then I want to do BK sub 2. So BK sub 2 says, look at the labels 2 and 3 here. They're on incomparable elements, so I can swap them. If I swap them, okay, that takes me to 1, 3, 2, which is down here, because I've swapped the 2 and the 3. And so that corresponds to just moving down through here. So this is like BK sub 1, and then BK sub 2. And now I have to do this BK sub 3, which always does nothing. But again, this doing nothing, you can think it's kind of like I tried to swap, well, okay, yeah, basically doing nothing in this case corresponds to this reflection here. Okay, so I did nothing and I stayed inside of the 1, 3, 2, but that's like reflecting off of this side of the hexagon. Okay? So now I'm here, I'm at the 1, 3, 2, so I've done ProMotion. This is one ProMotion. But I can keep doing this. I can say, okay, now I'm going to do ProMotion again. So I'll start by doing BK sub 1. If I do BK sub 1, the 1 is below the 2, so I do nothing. But that's like saying I was trying to swap the 1 and the 2, which would have moved me over here, but I'm not allowed to go there because I can't leave the blue region, so I have to reflect. And okay, maybe my angles are not great, but it's supposed to be something like this. Okay, yeah, like the drawing is not perfect, but you can sort of imagine it's bouncing like this. And then I do BK sub 2, which swaps the 2 and the 3. And that corresponds to moving through here. And then finally I do this BK sub 3 again, which does nothing, and that corresponds to reflecting off of here. And if you just keep doing this, you'll end up going like this. And so there's actually like this beam of light in this rhombus, and it's encoding, or it's basically following behavior of ProMotion. So, I mean, this is kind of a stupid example because it's like just two-dimensional and the poset only has 3 elements. But the fact is that you can actually do this for any dimension. So I'll try to write out something about like how you set this up. Okay. Or, yeah, here, I'll do it here. So let's let V be the set of points x1 through xn in Rn, such that the coordinates sum up to 0. So if you remember when we talked about the sort of standard representation of Sn, which was the representation living or corresponding to the Young diagram, which was like n minus 1, 1. Right, so there was this irreducible representation, and it was n minus 1 dimensional, and it sort of naturally lived in this space. And that's relevant for what I'm talking about here. So this is our space. And I want to consider these hyperplanes in this space, which are, okay, so I'll denote it by h, I, j, k. This will be the set of points in V. So the sum of the coordinates is 0. And I want to assume, so it's the set of these points such that xi minus xj equals k. So this is going to be some hyperplane inside of V. And I'm interested in the set of these hyperplanes where, maybe I'll call this like, okay, let's take H sub n. This is called the braid arrangement. And H sub n is the set of these hyperplanes H, I, J, 0, where I and j are between 1 and n. So in other words, these are just like, so what does this mean if k is 0? That's just saying xi equals xj. So you pick some I and j, and you look at the set of points in V where the ith coordinate equals the jth coordinate. That's some hyperplane inside of V. And then the set of these hyperplanes is the braid arrangement. And the picture, okay, again, I can only draw two-dimensional pictures, but for n equals 3, this looks like this. So it's like H 1, 2, and H, or I guess with a 0 superscript, and this is like H 2, 3, 0. Okay, so like there is a way of drawing it in this way. I guess I should say like this is two-dimensional. If n is 3, this is two-dimensional, and there's like a way of choosing your basis in a correct way so that if you draw it, you can make it look like this picture. So that there's some way that this is correct. Okay, so this is the braid arrangement. You can see it kind of looks like this. I mean, this picture, I really just took the braid arrangement, but I kind of just chopped it, like I just restricted it to this hexagon. And so what I've actually done is I've taken what I'll call H and tilde. So this is called the affine braid arrangement. Okay, maybe I'll say this. So this is the braid arrangement. And it's related to like the braid group. Like you've heard about like braids in like topology and stuff. This is related to that. And then this is the affine braid arrangement. And it's just the set of all of these hyperplanes for all I and j between 1 and n, where k can be any integer. So it's the set of all h, I, j, k, where 1 is less than or equal to I, less than j, less than or equal to n, and k is just an integer. Okay? And if I do this for k equals, or for n equals 3, so these are my hyperplanes with k equals 0, but then you end up getting like translates of these hyperplanes. So you would get something like this, and this, and this, and it would just keep going. You'd also have like this, and okay, I haven't drawn it super well. Let's see. The point is you get like a normal, like a usual triangular grid. Okay, so maybe like that. something like this. Okay, and my original braid arrangement was these here, right? So this was like my braid arrangement. And you can see I have my little hexagon sitting inside of here. So I've got this hexagon. So the way that you can think about this hexagon is I've taken the region which is bounded by like H, okay, so the hexagon is bounded by Hij -1 and Hij 1 for all I and j. Okay, so one of these is like H, so maybe this is like H131, depending on my conventions. Okay, let's just say it's that. This is like H13 -1, and then here we'd have like H121 and H12 -1. So you get these 6 hyperplanes which are bounding this hexagon here. Okay, and the same is true in higher dimensions. So here I'm thinking of this little hexagon as like a copy of the symmetric group S3. But in general, for any n, you'll have this n-1 dimensional space. You can look at the affine braid arrangement. You can take this polytope bounded by the hyperplanes of the form Hij -1 and Hij1. So this is some polytope containing the origin. And you can think of that as like a little copy of the symmetric group Sn, where it's like split up into these little simplices called alcoves, and those alcoves correspond to the permutations in Sn. So in general, the number of these alcoves inside of this polytope will be n factorial. And I guess the way you can see that it should be n factorial is that, like, okay, what does it mean to be in one of these alcoves? Like, how do you determine one of these alcoves? Well, basically for each hyperplane in the braid arrangement, like in this case for each one of these 3 lines here, I have to decide which side I'm on. I can either be on this side or on the other side. And you can think of that as determining, like, for the integers I and j, I'm deciding which one comes first in my permutation. And if you've decided for all I and j which one is supposed to come first in the permutation, then that's equivalent to choosing a permutation. Okay? So these correspond to permutations, and then you can play the same game where you can pick a convex union of these little alcoves, and that will actually correspond to the set of linear extensions of some poset within elements. And then you can do promotion by actually like drawing some beam of light that bounces around in this way. Okay, let me see. So maybe I'll mention another thing you can do is, okay, so here you can see I have like a bunch of these hexagons, right? So I have like this hexagon, but there are like all these translates, like I'm just tiling the plane with hexagons. And the same is true in higher dimensions. You have this little polytope corresponding to the symmetric group, but actually you can tile your n-1 dimensional space with these little polytopes, which are like little copies of the symmetric group. And then you can quotient out by this lattice, which is like the centers of these polytopes. Okay, so inside of this space, I have this lattice, which are the centers of all of these hexagons. I think actually, if you coordinatize it, these lattice points are actually just the points in V that have integer coordinates. Okay, so you take the set of points with integer coordinates, which are these points, you can quotient by that lattice in like a topological way. Okay, so like in topology, if you have an n-1 dimensional Euclidean space, and you quotient by a lattice, it's like a topological quotient map, you end up getting an n-1 dimensional torus. So in this picture, I can quotient and I get a 2-dimensional torus. So actually you can think of, okay, so this hexagon here is a fundamental domain for this torus. So you can think of this hexagon that I've drawn here as a torus. Okay, so this is a torus where I've glued together opposite sides. So like this side here is glued to this side. And then this side is glued to this side here. And this side is glued to this side here. Okay, that actually is a torus. Like usually when you think about a torus, like usually people define it as like you take a square and you identify opposite sides. Okay, that is one way of getting a 2-dimensional torus. But it turns out this is also a torus. And the easiest way I think to see this is that this is coming from this picture. You're taking a Euclidean space, quotienting by a lattice, that is a torus, and the fundamental domain is this hexagon here. Okay? Right, so you can see like this piece of this torus should be identified with this piece of, like this is like the bottom left part of this hexagon, so it should be glued to the bottom left part of this hexagon when I do the torus, the quotient. So these two pieces should be glued together, which is what I did here. Okay. Right, so now, okay, we can think of this as a torus, and then one of the nice things about this billiards perspective is you could say, well, what if I did the same thing, but I did it in a torus? Like now, instead of having this like boundary here where I do nothing when I do this Bender-Knuth involution B case of 3, so I like have to reflect off of this. What if the beam of light is allowed to like wrap around, and move around in the torus? And this leads to something that I call toric promotion, but I don't know if I have time to, maybe I can define it, and then maybe I'll see, I can talk about it more next time. Well, okay, maybe I'll say this. What I want to do is, I want to take my hexagon here, and I want to define, well, which is a torus. Okay, so my hexagon is a torus. And it has these toric hyperplanes in it. So this here is one toric hyperplane, but it's actually the same as this. This is one toric hyperplane in red, because like this piece gets glued up here, and then it continues down here, which gets glued over here. So this is actually like one toric hyperplane, and it's the image under this quotient map of all of these lines of positive slope. Like all of these lines of positive slope, when you quotient into the torus, they get sent exactly to that red union of like this red toric hyperplane. And similarly, there is this blue toric hyperplane. And then there's the green toric hyperplane here. Now there are 3 toric hyperplanes, and that corresponds to the fact, well, basically there are 3 choices for I and J, right? They basically correspond to the hyperplanes in the braid arrangement, and there are 3 hyperplanes in the braid arrangement, which are H12, H23, and H13. And so I can identify these 3 toric hyperplanes with vertices of a graph. So let's say I have this graph, or not vertices, edges of a graph. So I have a complete graph with vertices 1, 2, and 3, and this red, I think, is what I was calling H12, so that's like an edge between 1 and 2, here. And then the blue is like H2, 3. So it corresponds to 2 and 3. And then the green corresponds to 1 and 3. Okay, so the point is that we have a torus. In here it's 2-dimensional, but in general it'll be n minus 1-dimensional. It has all these toric hyperplanes. And the toric hyperplanes correspond in a natural way to edges of a complete graph. So what I want to do next time is say, what if I only choose a subset of the edges? Well, choosing a subset of the edges of a complete graph is the same thing as just choosing a graph. Okay, so I'm just going to choose a graph with vertices 1 through n. And that's the same as choosing a subset of these toric hyperplanes. And then I'm going to consider the billiard system that I get by doing basically this. But the rule is now, whenever you hit one of the hyperplanes corresponding to an edge in my graph, you have to reflect off of it. And whenever you hit a hyperplane that does not correspond to an edge in the graph, then you just pass straight through it. Okay? And then we're going to see that, okay, the beam of light bounces around in some way, and maybe I'll say a bit about what it does. Okay, but that's all for today.